we know the label is p. We call it p orbital. L equals 1 is a p orbital. Doesn't matter what n is. As long as you have L as 1, it's a p orbital. Of course, if you have n equals 3 and it's a p, that would be a 2p orbital, or a 3p orbital, or 4. That's just another label. So that p orbital looks very different. So this is a wave function. The wave function goes to 0, so this is plus and minus, plus minus, plus minus, plus minus, plus minus. But there's the node. And you remember, one-dimensional, you had that full wavelength, there was that node. It just looks like it, actually. It goes up and down, and up and down. Okay? So this is your standing wave, and it has a node, but this node is a radial node. So the radial node, it's a node, sorry. We see that node, this is an angular node, it's not a radial node, okay? The total nodes is n minus 1. So how many total nodes can we have if n equals 2? 1 total node. Now the differentiation is, the angular node, the number of angular nodes is L. So if L equals 1 in this case, that is 1 angular node, okay? And now, m sub L, what can that be? Minus 1, 0, and 1. Some of you are with me still? Some of you are with me? Good. I don't expect that everybody is with me, but I'm doing my best, I'm struggling, okay? So we have that angular node, and so then we have m sub L. It gives you the orientation. So this is one orientation, isn't it right? It's in the y direction. Couldn't I have one that's oriented like this? That's like a dog bone or a head or something like this? It could be oriented like this, and another one could be oriented like this. So this is why m sub L is minus 1, 0, and 1. So I have 3 different directions in space, x, y, and z. So I have one s orbital. I have 3 2p orbitals. Okay, that's what I have here. There's 3. Now if n equals 3, now let's go further with this first. There's the p x. This is the angular node. Where's the angular node here? It sits between here. There would be the other angular node. M sub L is 0. And minus 1, 1, and 0. This would be the p set. Okay? Minus 1, 0, plus 1. 3 of them. All right? Of course, they are not flat. They're spheres, so spherical. So if you have n equals 3, you have L equals 0. What is that? S. L equals 1, what is that? P. And L equals 2 is, it says right there, D. Okay? If you have n equals 4, what would be L? 0, 1, 2, 3. What would be, then this would be 4S. If that's 4, 4P, and 4D. And that's about as much. Now we can go to F, actually. So L is the number of angular nodes. So how many angular nodes do you have at L equals D orbitals? How many angular nodes can you have? 2. And how many total nodes? 2, exactly. So both of these nodes are angular nodes. That's how you can differentiate. So there is again another depiction, like you are a lousy dart player. You hit this here. Okay? And so the electrons would hit that like this here. That would be the p orbital. It would be in the x direction in this case. Okay? That's how you can see the probability. That's we sort of fade this out, that it sort of gets all one. But essentially it could be here, could be here, could be here, could be here, could be here. If you look at it as a particle. But actually it's a wave. Now this would be a 3p orbital. 3p. How many nodes do we have? 2 nodes. 2 nodes. And what are these nodes? Yeah, angular nodes. Exactly. Right. So now here it is. That's the number of orbitals. The orbitals, these are, what is n? N stands for what? For the principal quantum number, and n stands for what? For the energy. N equals 1 compared to n equals 5. That 5 is a much higher energy. Okay? And with this you have more orbitals possible. So if you have n equals 1, L equals 0, you have the designation that's a 1s orbital. You take the 1 before, and this because L equals 0, that's s. M sub L is 0, you have 1 orbital. Okay? If n equals 2, you can have more orbitals. You have L equals 0, which this is s again, but because n is 2, that's a 2s orbital. And M sub L is 0, there's 1, 2s. But then you have L equals 1 because n equals 2, n minus 1 is L. Okay? So that means you have a p orbital, and because it's 2, it's a 2p. And what is M sub L can be? It goes from minus L to plus L over 0. So there's minus 1, 0, and plus 1. So each of them is one direction in space. So this is 1, 2, 3 orbitals. So you're in the 2, primary quantum number 2, or principal quantum number 2. How many orbitals can you have altogether? 4. 3 p orbitals, 1, 2, 3, and 1 s orbital. Primary quantum number 1, how many orbitals can you have? 1 s only. Primary quantum number 3, you can have, okay, L equals 0, that's the 3s. Of course, there's s is only always 1 only. That's 1. Then you have 3p. How many p orbitals can you have? X, y, and z. How many is that? 3. Okay, and now we're going to come to the d orbitals. D is L equals 2. We said this is labeled d if L equals 2. So it goes from minus 2, minus 1, 0, 1, 2. There's 1, 2, 3, 4, 5 d orbitals. 5 different shapes of d orbitals. How they sit in space. Okay, so you have here at the third level, how many orbitals can you have? 5 and 3 and 1, 9. You go to primary quantum number 4. So you always have the 4s. Okay. How many nodes would have the 4s? N minus 1, 3. What would these nodes be for s? Radial or angular? Radial, because L equals 0. Okay, there's no angular. All right, and then you have the 4p again. You have L equals 1. You have 1, 2, 3. Minus 1, 0, 1. Then you have the 4d. You have 5 of those. And you have the 4f. You have 7 of those. Minus 3, minus 2, minus 1, 0. So you have 7 and 5 is 12. 15. You have 16 possibilities of putting that one electron into energetic levels. Okay, that's all there is. Now let's have a look at B-space. 1 second. Did you look at B-space? Some of you, I put an applet and another thing on there. And I want to log in there now. You didn't, huh? It's too far away from the midterm. Okay, so this is my B-space site. That's what I'd like to see. And you're getting it, whatever, also here, okay? So we go, here this will be your iClicker data. You can check if you have your gradebook and check if you have a 1 or a 0 there, okay? Doesn't mean you have 1 point, it only means you're present. So, M1A lecture, that's me here. Is it doing something? It's waiting, okay? Now you see here, I have an orbital viewer and a 3D orbital applet. Anybody ever looked at Dr. Quantum? 6, 7, 8, 9, 10? Okay, it's fun actually, you would understand it. Okay, let's go to the orbital viewer. That's a little more boring. Out blank, about blank? No, I don't want about blank. Connecting to Berkeley B-space. It should connect me. This morning it did it. Is that the orbital viewer here? So everybody's in B-space, huh? That's not good. No, that's not it. So let's see if we can see the applet. It was just there, wasn't it? There it is. Ah, okay. That's more fun anyway. So let's play. N equals 1. N equals 1. What could S be? What could L be? 0. So there's nothing else in that tab. L equals 0, nothing else there. Okay? Now this the x and y and z axis, I can rotate this thing now. It doesn't do anything because it's a sphere. Okay? All right? Now, let's see. Let me upright this again. It's rather sensitive. All right? Now let's see n equals 2. What can we have? No, not 3. N equals 2. These are... I will get it. Never give up. Aha. So let's do a slicing through this thing. N equals 2. That can be L equals 0. That's an S orbital. Let's slice to this. Show a slice here. No, that's not a good slice. Let's show it. We want to have... This might be a good slice. Yeah? No, not very good, actually. So you can play with this. You say no slicing, okay? And so now I can turn it around. You see, it goes, the color changes because it's oscillating. These are true calculations. While we're doing this, they calculate this somewhere in a computer. At least that's what they told me. And you see that? You don't see anything here because it's the same. It's a sphere. And the sphere has one space in there that is like the babushka where there's nothing, okay? Where the wave function is 0. So it has, what do you call this thing? Radial node, okay? Now, what is the other possibility? L equals 1. So then it becomes a p orbital. So you can have a p set, okay? Set is this direction. See, it changes. The wave function changes. Yeah? It goes up and down and up and down and up and down. So the p set would be this direction. Now, if I go to p x, that's that direction. It's because I have it here sitting like this. So it says right here, it's y is this direction, x is this direction. Of course, you can define it as you want it. Yeah? But there's a definition. I know that was the py. Where's the py? Let's see. No, I want the py. So that sits on this way. It sits this way. We're looking sideways on it. See it? Now let's turn it a little bit. Can I turn it here? Yeah, I can turn it here. See that? What's this here? What's this called? An angular node. Now, if I look at this from this side, let's see. It's sort of obscuring itself. But I can have it perfectly. That would be a y. You see, here's my y-axis. I put it upside down. Not really. That's the y-axis. Here it is. Okay. Now let's go to number 3. N equals 3. These guys. N equals 3. What can we have? L can be 0, 1, and 2. Okay. S, P, and D. Is that right? So let's see what it shows us. L equals 1, 0. L equals 0. No, 0. 0. Okay. How many radial nodes does it have? 2. Excellent. Now we go L equals 1. That must be then the p electron. How many of those we have in the third level? How many p electrons? No, how many p orbitals, not electrons. How many p orbitals? 3. Minus L, 0, and plus L. Okay? Minus 1, 0, and 1. And so let's see. Let's go around. Looks funny. See that? It has, so how many nodes does it have? Angular nodes. That has 2 angular nodes. And how many total nodes? Total nodes is n minus 1. So 3. Total nodes is also 2. So all the nodes are angular. All right? So now let's look at how many do we have here? So they look different, the p orbitals in 3p than in 2p. Like it's the px. Let's rotate this a little bit. Same shape, but different orientation. And the py. There you go. So we have 3 of those. Now, if L equals 2, so let's see, what do we see here? Oh my gosh. See that? It has a halo. Yeah? So there must be, how many nodes can it have? N minus 1, so it has 2 nodes. And how many angular nodes does it have? 2. These must be angular nodes that you see here. Now, so how many orbitals we have a total in D? 1, 2, 3. Look at this one. This looks funny. Yeah. See that? So now we project it this way. So there are 5. Okay? So how many angular nodes do we have? If I have, what is this? N equals 3. Again, 2 angular nodes. We've been doing this for a while here. Yeah? So let's go to N equals 4. Now we're getting very high energy here. N equals 4. So you have S, P, and D orbitals. They look different, of course, because they're in a high energy state, different wave function. We can look at those here. But the S orbital, how many radial nodes would that have? N equals 3 or N equals 4? I wanted to go to N equals 4, didn't I? Yeah, N equals 4. N equals 4 has how many radial nodes? If I have the 4S has 3 radial nodes. Okay, so that would be L equals 0. Okay, look like this. Yeah, that's sure. Then L equals 1 would be the P orbital. Let's play with this a little bit. Very complex. You see that? L equals 2 would be the D orbital. Look at this. Okay. This is the solution of these wave equations. If you do the Schrödinger solution for the Schrödinger equation, you can imagine there's quite a bit of calculation. Yeah? And I don't expect that you can draw this, but you should be able to recognize a 2p orbital, or an s orbital, or a d orbital. Okay? Or you should be able to tell me what's the number. Now let's look at the f orbitals. So we need to have L equals 3. We go to the f orbitals. And how many do we have there? How many f orbitals? 7. See, there they are all. Let's look at this one here. Oh my god. Okay, so we look from this side. You can rotate it, play with this a little bit, and you will get the hang of this. All right? Now we're not finished. Okay? So I'm going to show you the pictures one more in an easier way, and in a more... Now it's up here. See there, that's a simple thing here, so we can do that here. That's the 1s. Okay, that's the 2s. Come on. 2s, 2p. Okay, let's do the talkies here. Okay, let's do this here. We have here the 3D. You have seen this now. Okay. So that was the 3D, again, the dartboard representation. And then we have the 3D, so this is easy. You see that here? Okay, very strange looking. So 5 3D orbitals, and the 4 F orbitals, you see this, I've shown them here. You've seen the projections of some of those. And these are there's 2, 4, 6, 7. Okay, that's about as much as you need to know. There's 5F also, which looks similar. Now let's give you a question. Which has the most radial nodes? The 4F, the 3D, or the 2S? Think about it. So what is L here? What is L here? And what is L here? Angular nodes is this here, total nodes is this here. The difference must be obviously radial nodes. So you get the hang of it, huh? Good. It's not easy, but you got to practice a little bit. It's pure combinatorial, purely combinatorial. There will be a question about this in the midterm. Several, actually. Yes. I hate to do this to you, but there will be a question. I have office hour today from 4 to 5 and from 5 to 6, okay? Same place. Yes? There are 40 questions on the midterm. Oh, there may be a couple. Yeah, I don't know. Okay, let's see if you get this. Tomorrow, what day is Wednesday. Tomorrow is, okay, you need to practice. You need to really practice. Next time I'm going to ask you this again, and I want to see this properly answered on Friday, okay? Friday I do a review of everything. We can talk about this. Huh? See you on Friday. And the review session is here in Pimentel, yeah? 5 to 7, not in Twinell anymore. Yeah? Review session is in Pimentel. Okay, tomorrow 5 to 7. Do not go to Twinell.